Look at this recurrence relation. an is equal to an minus 1 plus 2 times an minus 2. My question is, assume a0 is 2, a1 is 7. Okay, you start with 2 and 7. You can compute what is a2, what is a3, what is a4. But my question in general is, do you have a closed form for this? What does the word closed form mean? You saw this, right? If an is 1.1 times an minus 1, given the initial condition that a0 is equal to 1000, if you remember, right? We could find a closed form for an in the example that we discussed a while before, right? Similarly, when an is an minus 1 plus 2 times an minus 2, with a0 being 2 and a1 being 7, can you give a closed form, a formula-like thing for an? The question can actually be generalized. What do I mean by that? By that I mean, if an is given to be some constant times an minus 1 plus another constant times an minus 2, these constants were 1 and 2 here in the problem's case. But in general, if I ask this question, if an is c1 times an minus 1, some constant c1, plus some constant c2 times an minus 2, then what can you say about an? There's a very neat way to solve such problems. And the method goes like this. Look at this c1 and c2 and construct a quadratic equation with c1 and c2 like this. Write down this quadratic equation, x square minus c1x minus c2 is equal to 0. And solve this quadratic equation. Okay? And you will get, let's say, two roots, x1 and x2. And assuming that these two roots are real and are distinct, things are getting very complicated, but don't worry, you will understand once we write an example and then see it. The story so far is, if an is c1 an minus 1 plus c2 an minus 2, simply pluck out that c1 and c2 and create this quadratic equation x square minus c1x minus c2 equals 0 and find the roots of this quadratic equation and call these roots x1 and x2. The solution will always be of the form an is equal to alpha 1, some constant alpha 1, times x1 to the n, x1 being one of the roots, plus alpha 2 times x2 to the n. This is the closed form. This is the formula for an. Okay, alpha 1, alpha 2 are constants, and x1, x2 are the roots of this quadratic equation. This is always true. Let us try to see this in action for this question. I don't know whether this theorem is really true or not. Let us try applying this theorem on this small problem, see how it works, and then go ahead and prove the theorem. Let's recollect the problem. an is equal to an minus 1 plus 2 times an minus 2, with a0 being 2 and a1 being 7. Let us write down the quadratic equation. So pluck out the 1 and 2 here, the constants that are sitting in front of an minus 1 and an minus 2. You get the quadratic equation. X square minus 1 times x minus 2 is 0. Solve this. Plug in the quadratic equation formula, minus b plus or minus square root of b square minus 4ac divided by 2a. Putting all the values, you will get x equals 1 plus or minus square root of 1 minus 4 times minus 2 whole by 2. 2 times 1 rather, which is equal to 1 plus or minus 3 by 2, which will give you 4 and minus 1 as the roots. Now, going by the theorem that we stated, the answer would be, the general solution, I mean the closed formula would be an is equal to some constant alpha 1 times the first root 2 to the power of n plus alpha 2 times the second root minus 1 to the power of n. The roots are 2 and minus 1. Correct? Now, what are these alpha 1s doing here? What are those constants? Now look at this. We have a0 equals 2 and a1 equals 7. Plugging that in, you can find out what is alpha. How do we do that? a0 is 2 and 2 will be equal to alpha 1 plus alpha 2 whenever you plug in n equals 0. Correct? 2 equals alpha 1 plus alpha 2. Similarly, a1 is equal to 7, which is equal to alpha 1 times 2 plus alpha 2 times minus 1. So, solving this, you will get alpha 1 equals 3 and alpha 2 equals minus 1. So, you now know what is alpha 1 and alpha 2. Plug that in, you have the solution that you want. So, an is going to be equal to, in place of alpha 1, plug in 3 times 2 to the n minus 1 to the power of n. Now, look at the power of this theorem. It helped you solve the given recurrence relation, and it helped you find a closed formula. An equals 3 times 2 to the n minus 1 to the n is such that you plug in n equals whatever value, you will get the answer immediately. It is not in the recurrence relation form. You have solved the recurrence relation. How did you solve it? You employed the technique that the theorem suggested. But how do you know that the theorem is true? Let us now go ahead and prove the theorem, and let us understand how this theorem is in general true always.